Hello, everyone, and welcome to the Laboratory Automation and Testing virtual event. My name is Katherine Elvira, and I am an assistant professor and Canada Research Chair at the University of Victoria in Canada. And today we're presenting on lab-on-a-chip technologies for drug discovery. Please feel free to submit any questions during my presentation, and I will follow up with you via email afterwards. So, today we're going to kind of go over the basics of what microfluidics is. So what is a microfluidic chip or a lab-on-a-chip? We're also going to talk about a specific subsection of microfluidics called droplet microfluidics. And then we're going to go into what is perhaps the more interesting side is how do we use these droplet microfluidic devices in the field of drug discovery. Okay, so on this slide that you can see a beautiful picture from elfo.com. It is the title actually I stole from someone. It's Stingy with Sample, and I think that really encapsulates what microfluidics is. The idea here is that instead of using huge samples to do chemistry or biology, we're using samples on the scale of nanoliters or picoliters. Okay, so a more standard definition, if you want, is there on the slide. It's the manipulation and processing of fluids on scales below 500 micrometers. So if you want to compare that to something in real life, scales below 500 micrometers are kind of on the scale of a human hair, okay? So when I say chip in this presentation in the context of lab-on-a-chip or a microfluidic chip, I don't specifically mean something with an electrode on it or something that you would put into your computer. What I actually mean is the science of small plumbing. So what we do with our microfluidic devices is that we create architectures on the chip that look like pipes or valves, and we use those architectures on a chip to be able to manipulate fluids, to be able to do chemistry and biology on really tiny scales. Okay, and that's why we call it the science of small plumbing. So in that image again on the slide here, you can see a typical microfluidic chip. It's made out of a clear polymer called PDMS, or polydimethyl siloxane, and then you can see that it's mounted on a microscope slide on top of a microscope objective. That's where the light is coming from effectively, and then you can see those pieces of tubing going into the microfluidic device, and those are effectively how we get our liquids onto the device, and then we use the device to do the manipulation of the liquids for chemistry or biology. And I think a really good way of thinking about this, if you're not a microfluidics researcher, is to think back to your days in the chemistry lab, if you ever went there, or a biology lab, and you think, okay, I used to do chemistry or biology in round bottom flasks, or I used to do biology in 96 well plates. Well, we're kind of doing the same idea, but instead of us using our hands to manipulate fluids to do reactions, we're using a microfluidic device to do that manipulation. So moving on to the next slide, this one kind of tells you some of the advantages associated with microfluidic or lab-on-a-chip systems. And I've picked out here the ones that kind of are themes, if you will, throughout my presentation. And the idea is that there's lots more. If you're interested, you can see the paper referenced at the bottom of the slide. But what my research really is concerned with is using tiny reagent volumes, so beyond the scale of nanoliters or the scale of cells. It's high throughput, so we're able to do our reactions at hundreds or thousands per second. It's enhanced experimental controls. So can we do things on a chip that we can't do without the chip or off chip? It's efficient heat transfer, so we're not going to go into that in too much detail, but the idea here is that we've got such small volumes of liquid that any heat we want to put into that system will take out is a really fast process. And the final one there is small footprint. And this is kind of a bit tongue-in-cheek, because if you read the literature, you'll see lots of beautiful images of a chip and how we can use them. In fact, I presented one in my previous slide. But the idea behind it is that actually there is a lab around the chip. Okay, so we are mounting our chips on a microscope, and we have pumping systems over to the side. So even though microfluidics definitely can be used outside of a laboratory setting, this is not something that I will be talking about in too much detail in this presentation. So let's go back to basics. I'm not going to go too deep, but it's a good idea to understand what really is microfluidics. Okay. So on this slide, you will see an equation for the Reynolds number. The Reynolds number is one of the most commonly used dimensionless numbers in the field of microfluidics. This is both good and bad. It means that there are lots of other dimensionless numbers that we can look at, but we're actually a bit focused on this one, so that's probably the downside here. But what we wanted to do in this paper that is referenced at the bottom of this slide is kind of come up with a standardized definition of what really means, what it really means to be working on a microfluidic scale. Okay? So again, this is one example. We used other dimensionless numbers, but the Reynolds number, I guess, is the easiest one to understand. Okay, so it's the ratio of inertial or viscous force to viscous forces on a microfluidic device, or those fluids on the microfluidic device, and it basically takes into account the density of the fluid that we're using. It takes into account the velocity of the fluid as it's pumped through the microfluidic device, and also the fluid's viscosity. But it also takes into account the characteristic dimension, or D, of your microfluidic device. And this is normally the smallest dimension on your device, okay? And then we know this, and we know that that's fine, but we also know that the characteristics of microfluidic flow are perhaps not always found in all of the microfluidic literature that you find out there. So what we wanted to do is say, okay, what does the microfluidic research community define as microfluidic, and how does that balance with what we know about fluid flow on that scale? So that graph that you can see down there is us doing a virtual experiment, if you want. What we did is we built a model, and we wanted to look at a plastic capillary that is 5 meters long, and we wanted to just flow fluid through it, and we wanted to virtually measure different Reynolds numbers at different residence time, and that's just a proxy for flow rate, how fast are you pumping through your microfluidic device. And as you can see, there are 4 lines on that graph, and those represent characteristic dimensions, so that value D in the Reynolds number equation, that the literature uses within a microfluidic device and calls microfluidic. Okay? So it's everything from around 100 micrometers of that interior pipe dimension to around 5 millimeters on the top right-hand corner of that slide. And then what we did is we put a grey box over the graph, which represents the Reynolds number at which you're getting all the advantages associated with microfluidic flow. Okay? And what you can see is that for devices where your internal diameter is about 5 millimeters, you're really not gaining all the advantages associated with microfluidic flow on that scale. But conversely, on the other side, if you go down to 100 micrometers and your device is in that kind of range of dimensions, then you're getting the associated advantages of the Reynolds number with microfluidic flow. Okay, so this is one example of how it goes, and that's kind of how I came up with a definition on the first slide, or the second slide, I guess, of my presentation, saying that really it's below 500 micrometers where you get all the advantages associated with microfluidic flow. Okay, so that was pretty heavy. Let's move on to something a bit more interesting. So on this slide, what you can see is a very, very simple drawing of what a microfluidic device is. So I've put arrows so that you can see the direction of flow, okay? And then I've blown up a section of the device that we call T-junction, okay? So it's a bit faint, the lines, but what you have basically is you have your oil flow coming from left to right, you've got your water flow coming from the top and the bottom, and when they meet at effectively a T-junction, you get this stripping off of these droplets, aqueous droplets in the flow, and that is how we make microfluidic droplets. So this is a lot easier seen in the next slide, in slide number 6. And here what I've done is I've taken sequential images from a video so that you can see what is happening at the T-junction. Okay, so in the first one, you can see the droplet moving away, but in the second image there, you can see that water flow start to peak out into the oil flow, and it starts to get stretched in the third image, and then it buds off in the fourth and fifth images to form a final droplet in the sixth image. And at the end of my presentation, I will be showing a video of how we make our devices and what I do with them in my group, but also showing videos of these droplets in flow, and it will be a lot more obvious then. So why do we use droplets? So I've taken this from a fantastic paper by one of my colleagues back in Switzerland, and it's the idea of compartmentalization and being able to access specific parts of your chemical or biological system. Okay, so if you look on the left, you've basically got a design that looks like let's just call this a beaker in a lab, and in there we put, say, a couple of populations of different types of cells. So if you wanted to look for a specific cell in that system, you wouldn't be able to find it. There's too many of them, and they're just floating around in this big volume of liquid. So miniaturization, in the image one to the right, is what happens in droplet systems. We're miniaturizing the container or the volume in which these cells or molecules exist. Okay, so that's us compartmentalizing so that we can inject in each droplet what we want as reagents or as cells or as chemicals. Okay, and the final two images on the right of that slide are showing you how we can serially down process those microfluidic droplets. That's what I was showing you in those stills from the video and the slide before. And then if you want more output, if you want to be able to kind of produce something in bigger quantities, then you can parallelize these devices to get more quantification. Okay, so if you look up images of droplets, if you just Google microfluidic droplets, you'll see a lot of images like I'm showing right now on this slide. And you know, they're beautiful, they're spherical, they're self-contained, they're totally distinct, and they're constant volume. Overall, we say they have integrity, but I mean, if you look at those images, they effectively glow on the edges, they're so beautiful. Now, if you're actually a researcher that works in the field of microfluidics and you've been in the lab recently, you might be a bit more commonly aware of the images such as this one or this one. Okay, and I have picked the worst images that I could find to show here, but I think it highlights something that we do very much in science, and that is that we do show positive results and not negative results. So this paper that I cite at the bottom of my slide is me saying, okay, well, let's talk about the negative sides of this. What happens when things go wrong in microfluidic research? So what we did in this research was say, okay, droplets are really important, and they have the potential to really help us do science and chemistry and biology that we really couldn't do in any other way, and there's some fantastic science out there. But realistically, we know that they don't work so well in the lab, and we have issues with this. Okay, so what I did is I got a microfluidic device, a very, very simple one, very similar to the one that I showed earlier on, and I made a lot of different types of droplets with lots of different types of oil phases. The water phase was always water, and then I added what we call a surfactant, which is effectively a stabilizing molecule. Okay, so when you're at home and you're making salad dressing, you've got a jar and you add some vinegar, which is watery, right? And you add some oil, which is oily, and you shake it up. That's you forming droplets effectively. Then you know that as soon as you stop shaking, you get your phase separation again. So a surfactant would allow that droplet stage to not separate out, and that's effectively, if you've ever added mustard or something like that to your salad dressing, you know that when you shake it up, you don't get that phase separation again. So when I was doing this experiment, we were also changing around that surfactant concentration. And what we found is that we had around 20 what we call droplet failure modes with different concentrations and different types of surfactants and different oils in our microfluidic system. And here are some representative images, and what you can see is that they don't look like those beautiful droplets that I was showing you on the previous slide. So what we did with that data is we said, okay, fine, we have identified a lot of different types of droplet failure modes that are commonly seen in microfluidic devices. But why do they happen? What's going on here? So we kind of categorized them. We looked at whether these droplet failure modes happened in flow, which is the top half of this diagram here, or whether they happened when the droplets were stationary and in storage mode, which is the bottom half. And then we kind of looked at the underlying physical or chemical effect that was causing that droplet failure mode in the microfluidic device. So we're not going to go into this in too much detail, but I am going to bring up one droplet failure mode. Okay, the math is not so complicated here, but I'm also not going to go into much detail because I don't have time at the moment. But what we were looking at here is we were looking at that surfactant molecule. molecule, that stabilizer molecule in our droplet microfluidic system. So I have a diagram on the slide of a channel with 3 microfluidic droplets in it. And what you have to imagine is that your surfactant is floating around in that system, okay, normally in the oil phase, so in that white phase of surrounding the droplets. And that surfactant molecule is going to adhere both to the wall surfaces, but also to the surface of your droplet to stabilize it. So we built a theoretical model to look at how this surfactant is distributed within our microfluidic device, and that's the map that you can see below the image. And so the first line of that map basically looks at surfactant adhesion to walls as concentration. So this basically means all the available sites for adhesion of that surfactant to the wall surfaces or to the surface of your droplet to just look at as concentration. This is basic laminar kinetics that you can look up afterwards if you want. And we did some simple maths to figure out if we could look at the chances or the probability of that surfactant adhering to those different surfaces, but also what would cause that adherence to fail. Okay, so if you look at the right-hand side of the slide, right at the top, I have an image of a microfluidic droplet forming at a T-junction. And where that blue arrow is a droplet failure mode. It's called a dripping mode. And you'll see a bit more about this in the next couple of slides. But what is happening here is instead of the droplet forming cleanly at that T-junction, it is kind of sticking to the top of that channel and then budding off to form the droplets. Okay, and this is based on a lack of surfactant in the relevant sections of the microfluidic device. So then we have 2 graphs there on the right-hand side of the slide. And what it shows here is the experimental results. So we made a microfluidic device that had a dripping mode, and we kind of characterized how long it took to form the dripping mode and how many droplets we could put through our system. And then we did the same with the model. And the model I know has only 4 data points. That's because it was very intensive to run. But you can see that the same type of effect happens. You've got a steep increase at the beginning and then kind of a plateau. And the really interesting thing that this was telling us is that the fact that we have droplets, so aqueous systems in our channels, means that it's stripping the surfactant from the wall and causing these droplet failure modes, which is called a dripping. Okay. Now we thought that's fantastic. It's all very theoretical. What does it mean? And so on the next slide, what we can see is the following. Okay, so on the y-axis we have the relative abundance, so up to what's 120%, but let's say 100%. So how much surfactant is available there for coating your walls and your droplets. And then what we did is we theoretically, or in the virtual system, in our model, effectively, we pumped through droplets at 3 different frequencies. Okay, so the first frequency is 2 Hertz, 2 droplets per second. We're going through our device, which is really, really low. And you can see that over time, that nice blue graph at the top, there is a bit of a dip, but it stays at around 90% coating of your surfactant in the system. But then you can see that as we increase the droplet frequency in our device, every time there's less surfactant available for coating those wall surfaces. And that is why we get these droplet failure modes. Now, again, I really enjoy doing this type of research, but I'm more of a practical person. So I wanted to know if this model could help us do something practically in the lab, and it can, okay? So what I'm showing here is us using that theoretical concept that I explained in the previous slide to mend the droplet dripping failure mode in our microfluidic device. So the model predicts that when droplets are there, your surfactant coverage of the walls is not so great, but it also predicts that if the droplets go away, then your surfactant concentration goes back to scratch. And this is what we were showing here. So if you look at this slide, you have basically the sequential images from top to bottom, okay, of different steps in the experiment. And left to right is the image just before the droplet forms and just after the droplet forms. Okay, so at the top you have the device, it's new, it's running, and you can see that that droplet forms really cleanly at that T-junction. And then over time, as we add more water, more droplets into our system, you can see that that dripping failure mode starts to happen. Okay? You can specifically see that on the image on the right-hand side, because you can see it sticking. But as our model predicts, if we just remove the droplets, if we stop the droplet flow in our microfluidic device, then our system resets and our surfactant concentration shoots back up to 90 or 100%. And we call this a device recovery step. And you can see that after doing that, we get that clean droplet formation again. Then over time, as the experiment happens, you get that sticking again, and then you can repeat this process. So that was really exciting, because I really like kind of showing how what you would call as negative results, or from a grad student perspective, extremely annoying experimental behaviour can be used to understand the fundamentals of our system, and then we can use that knowledge to mend the system to get it working better. So from now on, I'm going to just give you 2 or 3 examples of how we can use these droplets, now that we understand what they are and how they work, in drug discovery. So we have, the first example is distribution coefficient measurements. So if you're a pharmaceutical company and you're developing a drug, it takes a long time, 10 to 15 years, it costs $2.6 billion, it's ridiculous. And you really want to know as much about that drug as possible, as early on in the discovery process as possible. Okay, so one of the tests you do really early on is that you get that drug and you put it in a shaking flask, as you can see on the bottom right of that slide, and you add an oil phase and a water phase, and you shake it up, and you check how much of the drug is in the water phase and how much is in the oil phase, and that kind of gives you a prediction of whether that drug will be happy going through the cell membrane into the cell. Okay, so you can do this computationally now as well, but that is the method, the traditional method of forming it. So what we wanted to do in this study was kind of highlight how you can do that on a microfluidic device, and do it better and faster and more accurately. But what we also wanted to do was show that we can make microfluidic devices not out of PDMS, that first image that I showed you right at the beginning of my presentation, but using a commercially viable technique called injection molding. Okay, so loads of the things that you have at home that are made out of plastics are made using injection molding, but not so many microfluidic devices have been made this way. We want to just show the capability of this system. So what you can see in the pink and blue image on the left-hand side is the design of the device. So we have very small features down to around 50 micrometers to make our droplets. These are small droplets. And then at the top of the device, that huge pink chamber you can see is basically on the millimeter scale. So it's really, really big for us. And this was a way of us dosing the droplets with our drug that we wanted to test, which was quinine. Making those droplets, we have really high surface area to volume ratios because the droplets are small, which allows us to get really fast partitioning of that drug between our water and our oil phase. And then we use that nice big chamber over there to separate out the droplets based on gravity so that we can have oil and water separately and do the characterization of where that drug is. So I'm not going to go into too much detail about the data here, but since we wanted to show that this was a commercially viable system, we spent quite a lot of time showing how this device works. So that's the graph on the left-hand side. So we're looking at basically different flow rates and looking at how those flow rates, whether those flow rates allow us to separate out those phases in that chamber at the top. And the dashed box at the bottom left shows you the regime, the flow rate regime, at which the separation is most efficient. And then on the right-hand side of this slide, we are comparing, as the little image on the top of the graph shows you, comparing the shake flask method, the traditional method, with our microfluidic method, and showing that the data is comparable to our bulk experiments, but also to the literature. And you can see that when we plotted the data for our experiment, which are those 2 violin graphs in blue and red on the slide there, and because we detect individual droplets, we actually get huge amounts of data for each data point compared to the bulk system. So to summarize this section right now, we compared basically the traditional method, so your shake flask method, with what we called our mini-fluidic reactor in several different categories, if you will. So the first one was the speed of the total experiment. So overall, traditionally, we would do that 24 hours to make sure you get full phase separation of the water oil phases, so you can quantify how much drug is in each phase. But in our mini-fluidic reactor, we only have to wait for 30 minutes. The whole experiment effectively took 30 minutes. There's, of course, a volume, a big volume advantage here. So we're normally using around 20 milliliters for each experiment using traditional methods. And for us, it's only around 300 microliters per experiment. The cost, obviously, if you're decreasing the amounts of reagents you're using, is a lot lower. And that even includes when you're using the chip as part of your costing analysis. And then I think the most important part for me here is what we call user sensitivity. Okay, so if you're putting a reaction on a chip, like we are, and trying to do a partition coefficient or distribution coefficient measurement there, then the user sensitivity is extremely low because it is effectively an automated process that happens on a chip. Whereas actually, if you do experiments yourself in the lab, and what you find many times is actually doing the experiment reproducibly between different people is harder. So there's an effect there as well. Okay, so the next example that I have is to talk about lipid digestion kinetics. Okay, so up till now, we've been talking about water droplets in a surrounding oil phase. And here we're going to flip those phases. Okay, so here we have oil droplets in a surrounding water phase. And the reason why I wanted to do this is I was collaborating with some researchers at the Laboratory of Food Sciences at ETH Zurich. And they were really interested in obesity. That's what they were looking at. And they had this inkling that the way that fatty emulsions were digested in your body had an effect on satiety. Okay, so by what I mean by this is that when you eat fatty products, in many cases they form emulsions in your digestive system, or they come as emulsions in food anyways. And so what they found is that when they did bulk experiments on these emulsion systems, they were very interested in how these emulsions interacted with each other under different digestive conditions. Okay, so what we did is we designed a chip. You see two images at the top of a section of that chip. The chip had a section to make droplets, and then it had a section that showed you had to trap these droplets. Okay, so you see those little traps with different amounts of droplets in each one. And on the right-hand side, you can just see the fluorescent image of the same section of the chip. And what we wanted to do was we wanted to trap either several droplets per trap or a single droplet per trap, and then see how the digestion happened and whether there was a difference between those microstructures of the lipids when they were interacting with each other, whereas as opposed to when they were not interacting with each other. And that's what you can see at the bottom. There's two experiments there. So in the top case, you have 5 droplets trapped. And what we would do is that then we would flow aqueous conditions that mimicked gastric and pancreatic lipolysis. And then we can quantify how those are digested over time. And then we did the same experiment, as you can see at the bottom, where there's only one of your lipid or fatty droplets per trap, and how those are digested again under gastric and pancreatic conditions. So the first thing that we actually did was double check that regardless of the amount of droplets per trap, you would still get the same flow conditions, right? We wanted to make sure that the effects that we would be seeing, hopefully, would only have to do with the fact that the droplets were interacting with each other or not, and not have to do with the fact that actually they weren't being accessed by your gastric or pancreatic enzymes, okay? And this is us doing PIV experiments, so particle image velocimetry experiments. And what happens here is you just flow through your device lots of fluorescent nanoparticles, and then you measure using software, it's all automated, how fast this particle moves. And then you can see these kind of maps, as you see here, specifically at the bottom, of what the speed is of your fluid flow under different conditions. And then you can see that with 1 droplet, 2 droplets, or 6 droplets, 5 droplets, sorry, the flow conditions are pretty much the same. So we were then confident that any effect that we see is to do with the interaction between those different droplets. So you can see this data on the next slide, and again, I won't go into this in too much detail, but what we're showing on the left-hand side is what I've been talking about. So how did the size of these droplets change with pancreatic or gastric glycolysis conditions? That's that line top to bottom in the middle of the graph. And then the filled spheres, the black spheres at the top, denote droplets that were multiple droplets per trap, and the bottom line, the empty spheres, the white spheres, is just one droplet per trap. And you can see that there is a difference in the digestion rate of these droplets. And we did some math to kind of quantify that, and that's shown in the graph on the right-hand side. And what we found is that if you have these droplets interacting with each other, they are digested 1.4 times slower than if they are just not interacting with each other. And that's interesting from the food perspective, because it means that we could design foods to be digested at different rates, and therefore your satiety is different and therefore help to combat obesity. But what I was really interested about from this study is that a lot of researchers use these types of fatty molecules or fatty droplets as drug delivery systems. And no one has a look at how these droplets interact with each other. But if we say a 40% increase in how these droplets are digested, depending on whether they interact with each other or not, then that's majorly going to affect also the drug release within your body. Right, one final example on the next slide, and this is what my group is actually working on at the moment, which you will see more about in the video after this slide, is called droplet bilayers. So we're going back to our water and oil systems here, and we're adding phospholipids to this system. You can see that kind of system on the top left of this slide. So phospholipids are the molecules that create your cell wall or your cell membrane. And what we're doing here is we're adding them to our water oil system, and because they're amphiphilic, which means they have a water-loving side and an oil-loving side, they self-assemble on the surface of our droplets to form monolayers. And as you bring them together in a microfluidic device, as you can see on the photograph to the right of that diagram, they form that kind of glowy structure in the middle, which denotes a cell bilayer, okay, or an artificial cell bilayer in this case. And so what happens here is that then we can dose one droplet with our drug or molecule of interest, and then see how it goes through our bilayer and quantify it in the other droplet. And that's what we're showing on the right-hand side of those experiments. Over time, you can see the bright field images and the fluorescent images, and you can see that over time, that fluorophore in the yellow droplets transfuses through that bilayer that we have created to fill your other droplet. So we're nearly done. We're now going to watch a 3-minute video about my research. It includes some really nice images and videos, I guess, of droplets and how we make our devices. And then I'll just wrap it up for you with the last couple of slides.
So the best way to visualize microfluidics is to think of a tiny little piece of plastic around the size of a postage stamp. And imagine on there you can build tiny little pipes and little chambers. Think about like the width of a human hair, so really, really small. And we use them to do chemistry or biology on really small scales. What we do is we build artificial cells on a chip. So we are very interested in the cell membrane. The cell membrane is kind of the skin of the cell. It covers the cell and it allows the cell to communicate with the outside world. And we build these artificial cells by building the cell membrane on these chips and using that to look at how drugs get into cells. What I'm really interested in investigating with our artificial cells on a chip is being able to predict how a new drug behaves in the human body before we put it into human beings. It takes around 10 to 15 years and around $2.6 billion to develop a new drug. And a surprising amount of new drugs fail when we try and test them in humans. There are a lot of things going on in the cell. The cell is really complex, there's lots of components, there's lots of proteins, there's lots of other chemicals around. And so you can't necessarily tell what part of the cell your drug is interacting with. So if we can predict how they're going to interact with human cells well before we need to do any testing in humans, we might be able to develop drugs faster and cheaper than we do so now. One of the things that we do on our microfluidic chips is build droplets. Okay, so droplets are like any drop of water, a raindrop, that's a droplet, but we make these on a much, much smaller scale that you can only see under a microscope. We do that on a chip and at really high throughput, so that means thousands of these droplets per second. So then once we've made these droplets, we can add the molecules that make up a cell membrane. It gives us a huge amount of control over the chemistry and the biology that we do. What we want to do is build these artificial cells to be as similar as possible to real cells, but we can identify and design exactly what components we want them to have. When I was an undergraduate student, it felt like this was the technology of the future, no? As you know, phones used to be these huge pieces of furniture almost that you would have in your house, and now we've got these tiny mobile phones. In the same way, I kind of think that, you know, now you're in a chemistry lab and you would probably use some glassware to pour some liquids together to do a reaction, but it's big volumes of liquid, and now we can do that on a chip with tiny amounts of liquids. So at the moment, they're very simple artificial cells, but the idea is that as we get better at building them, and we do more research in this area, we can make them really similar, at least to the cell membrane, to the cell skin of normal cells.
So I hope you enjoyed the video. That was made by Julian Sketchley. He's an undergraduate student at University of Victoria. He's also an amateur videographer, and we're really happy to have that. But also I'd like to thank my grad students and my collaborators, my grad students Ilana, Jamie and Keaton, for the fantastic work we do with artificial cells, and my collaborators there, my funding bodies, and thank you also for coming and viewing this presentation. If you want to know more about our research, we have a cool website and some Instagram and Twitter handles there, so you can follow us and see more about what we do and life in my group. Thank you for coming.